Depending on your purpose, there are different types of public key infrastructure certificates, or PKI certificates. These certificates are used to verify an organization's identity and ownership of the public key. A root certificate is the first certificate that a certificate authority, or CA, creates. This certificate is self-signed and is used to sign lower-level certificates, such as intermediate certificates. These certificates go through different processes to be approved, and the process depends on the certificate and organization. Subject Alternative Name Certificates, or SAN certificates, allow an organization to cover multiple domains. Wildcard certificates are like SAN certificates. Wildcard certificates allow an organization to cover unlimited subdomains. Code signing certificates are used by app developers to prove that an application is legitimate and hasn't been altered or compromised. When the user installs a program and there's no certificate, they receive a warning that they shouldn't trust the app. Self-signed certificates are certificates that haven't been validated and signed by a CA. These certificates are easy and free to make, but they don't provide the same protection and security as a CA-validated certificate. If a website uses a self-signed certificate, the user sees a warning when visiting the site. Secure, encrypted emails are generally sent using the S-MIME protocol. When you send secure emails, you need to know the recipient's public key, which you'd find in email certificates. These certificates are usually used within an organization that uses its own CA, but some public CAs also provide email certificates. You can use certificates to identify and validate individual users and computers. You generally see these kinds of certificates in a network environment where they're used to validate a computer or user to the server. The most common use for certificates is for websites that use SSL or TLS. These certificates validate that the website is authentic and secure so that users feel safe. When a site wants to purchase a certificate, there are 3 different validation levels a CA can offer. These are domain validation, organization validation, and extended validation. Domain validation is the lowest level and isn't very secure. A CA issues a domain-validated certificate to anyone who's listed as a domain administrator in the WHOIS record. The CA usually validates this with a simple phone call or email, which isn't hard to spoof. These certificates can be issued usually within a matter of minutes. An organization validation requires the certificate purchaser to not only prove that they're a domain administrator, but also that the organization is real. This process varies with each CA, but it's more in-depth than a domain validation. These certificates may take 1 to 3 days to be issued. Extended validation is the highest level of trust. An extended validation requires the purchaser to prove that they're the domain administrator and also requires a much more thorough vetting of the organization itself. These certificates may take 1 to 5 days to be issued. To fully understand how certificates work, you need to understand how CAs are set up. To increase security, CAs operate in a hierarchy of multiple CAs. This is done so that if one of the CAs is compromised, only the certificates it issued need to be revalidated. The first CA is a root CA. This is a self-signed certificate and is used to validate additional CAs. Under the root CA, you have subordinate CAs, also known as intermediate CAs. You can have multiple intermediate CAs based on their policies and regulations. The intermediate CAs validate the issuing certificate authorities, and the issuing CA is the one that hands out certificates. When you check the certification path in a web browser, you can usually see the structure. For example, we see that their server certificate was issued by this intermediate CA, which was signed by this root CA. This structure is known as certificate chaining or the chain of trust. Certificate chaining is done to protect the root certificate. If the root certificate is ever compromised, all certificates that have been issued underneath it are now invalid and need to be redone. Another common method of protecting the root CA is to keep it offline and only bring it online when it needs to authorize a new intermediate CA. Once the root CA has been set up and the intermediate certificates issued, the root CA is generally taken offline. This means that it's isolated from network access and is usually completely turned off. If an intermediate CA is compromised, only the certificates they issued need to be reissued. In other words, not every certificate that was issued under the root CA is compromised. The problem with this is that the root CA can't manage and update the certificate revocation list, or CRL, if it's offline. To remedy this, the intermediate CAs can be set up to manage the CRL, or a specific intermediate CA can be configured to handle this job. Instead of having browsers constantly checking the CRLs, the Online Certificate Status Protocol, or OCSP, was created to replace CRLs and can be used to determine the validity of certificates. Let's see how this works. When OCSP servers, also called responders, receive a request from the web browser, they check with the CA and send an up-to-date certificate status. This frees up CAs from having to maintain their own CRLs. To further help with performance, a network might use OCSP stapling. Stapling simply means that the server that holds the certificate also provides any revocation information. This works by having the certificate holder send a query to the OCSP responder at set intervals. Then, the server staples that timestamped response to its certificate so that in the first SSL or TSL handshake, the OCSP validation is already attached. Now, the user's browser doesn't need to perform a separate OCSP request. Keep in mind that it's possible for a man-in-the-middle attack to intercept certificates during the handshake. This would allow a hacker to set up a malicious site using a valid certificate. This can be prevented using certificate pinning. Certificate pinning is when an application, such as a web browser, has the server certificate hard-coded in the browser itself. When the application connects to the server, it downloads and checks the certificates. If they don't match, the application blocks the connection. Just know that certificate pinning was never really adopted by modern browsers, so it would mostly be used inside an organization that's running their own CA. Let's shift gears to trust models. All CAs start with a single trust model. It's also possible for you to set up a mesh model. In a mesh model, multiple CAs issue certificates to each other. This works great because if one CA is compromised, those certificates can still be valid because other CAs have authenticated them. The problem with this model is that it becomes extremely difficult to scale up with growth. Another thing to consider is how trusts can be set up when one organization who has their own CA structure wants to partner with another organization that has their own CA structure. In this scenario, there needs to be a way for each organization to trust the certificates issued by the other CAs. This can be done by setting up a bridge model in which both hierarchies trust each other. In this case, clients in both organizations trust certificates issued by CAs of either organization. You can also be more restrictive by setting up trusts with individual CAs that are lower on the hierarchy. Another common setup is the web of trust. Instead of using a CA, everyone is a trusted authority. For example, if Craig trusts Ethan and Lynette trusts Craig, Lynette will also have an indirect trust with Ethan. In other words, you trust a friend of a friend. We see this set up often in PGP. Implementing the proper model can help ensure that certificates are properly maintained and validated. Of course, all of this also relies on keeping our encryption keys safe. Keeping a backup of private keys is important, but you'll need to make sure that they can't be accessed unless absolutely necessary. Normally, the CA never gets their users' private keys. You can, though, use key archival to back up private keys. All this means is that the user sends their private key in a secure transmission to the CA to keep it safe. The problem with this is that a serious security breach can occur if private keys are compromised. The advantage is that the archive of private keys is readily available if any are lost or corrupted. Key escrow is like key archival, except that keys are sent to a trusted third party instead of the CA holding the keys. This is often done for security or legal purposes. Getting access to these keys may require legal action, and this is by design. For example, if law enforcement needs to access and analyze emails, they would need a court order to get the keys needed. That's it for this lesson.